0. There you go. Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin another of our monthly CoCoRaHS Weather Talk webinars. Thank you for joining us today. I'm your host, Henry Regis, and running the technical side of our program is Peter Goebel, who's filling in for Noah Newman, who is on vacation this week. We're coming to you live from the Colorado Climate Center here at Colorado State University in sunny Fort Collins, Colorado. For those of you who are unable to join us for our live broadcast, we'll be recording it for future viewing on our website, and that should be up online by Monday. All of our Weather Talk webinars are sponsored by listeners like you, donations from you guys, and we really appreciate that. Well, this is our 50th Weather Talk webinar. Wow, time has flown. It's hard to believe we've covered that many topics already. Well, today for our 50th, we're going to talk about weather and climate of the southeastern U.S., and that also includes Puerto Rico and the U.S. Virgin Islands. Many of you today live in the southeast or have lived there at one time, and you may be quite familiar with what our guest has to say, but in some cases you might be surprised. So here today, actually it's Bastille Day for those historians, the 14th of July. Here in 2016, we have the director of NOAA's Southeast Climate Center, Chip Konrad. And Chip's coming to you from the University of North Carolina at Chapel Hill. And I'm an NC State grad. That was our rival university, but we're really glad to have Chip with us anyway. Chip is an associate professor in the Department of Geography at UNC Chapel Hill. His research focuses on the atmospheric patterns associated with extreme weather and their impacts across the southeast United States. Well, Chip, welcome. It's a real pleasure to have you with us today.
Okay, thank you very much.
You know, I've heard through the grapevine that not only do you have a lot of interest in climate, but that you're an avid birder as well. And a lot of folks that are listening out there are birders, and then they go out there. What's at the top of your list so far of birds that you've seen?
Yeah, well, I'm just thinking here recently, I was in New Mexico, and it's always a great opportunity to go to another part of the country with the birds I don't know. And believe it or not, I'd never seen a black-headed grosbeak before. And anybody who lives out there will probably say, well, yeah, they're actually pretty common birds, but that turned out to be a life bird for me.
Wow, that's pretty neat. That's pretty neat. Well, I'm going to let you take it away, and we'll join you after your presentation with questions from our audience.
All right, thank you very much. So this is a great opportunity for me here to talk about the climate of the region. This is a talk I've given a number of times before. It's kind of an opportunity also to showcase some of the research that I've done in the past, and also research in particular that we're carrying out or carried out here at the Southeast Regional Climate Center. And I think basically the first thing I want to do here is just very briefly speak to our center. I think there have been 2 talks already from people from other centers, but the Southeast Center here, you can see our region here in the map. Our region basically extends from Virginia all the way down to Alabama and Florida, and then you can see that includes Puerto Rico and also the Virgin Islands, which isn't listed here. But we're funded by NOAA to carry out basically a lot of stakeholder-driven climate service. So that includes research, a lot of climate monitoring. One thing we're really an expert at is climate data, and particularly developing tools that translate that climate data into information that's useful to different stakeholders that we have in the region. And so just to kind of give you one example of a tool that many of you might find useful and some of you may already be familiar with, we have our Climate Perspectives tool here. And this is just a screenshot here of our of our website, and you can see the tool there. And just kind of as a real quick example, I don't have time to go through and show you how to use this tool, but I'm going to give you a URL to it here in just a second. But just as an example, if you just take a place, take New York City, and let's say if we basically go back in time to the end of February of 2015, many of you might remember that February 2015 was an extraordinarily cold month. And so one thing this tool is really good at is quickly putting the recent weather and climate into a context, basically comparing it with prior years to see basically how it stands out. And so if we look here at this particular station here at Central Park, and we look at Saturday the 28th, 2015, the high of 28, really 29 degrees, the low of about 13, is most equivalent to what you would experience in Anchorage, Alaska. And so you kind of get the idea here. Each row here gives a climate perspective for a longer period ending on that particular day. And so if you look at the entire month here of February, so basically the 1st through the 28th, you look here, you can say, okay, 32.1, that translates as a tie for the 7th coldest. That's pretty amazing when you consider that's a record of 140 years. And then the minimum temperature there averaged out close to 16 degrees, second coldest out of 140 years. And so that's most similar to what you would expect in Portland, Maine. And so, again, I don't have time to go through all the details of this, but this is just one example of the type of output that you can get from this tool. We also have map outputs of the tool, and I'm just going to show you one from February of 2015. So this is basically ranks of the mean temperature for that month across the whole CONUS. And you can see here towards the northeast, there were a lot of locations in which it was the coldest February on record, which is really amazing when you consider the fact that the climate really is warming. And then it's really amazing, too, that you go and you look at basically the western part of the country, and you can see that there are quite a few stations which were actually of record warmth. And so, anyway, with this tool, you can take, basically, you can look and see what's been happening here recently, how does it compare with the past, and also look across different parts of the country. And so here's basically the URL. We've got climate perspective set up for many, many stations in the southeast. And so you see the address there. And we also have it set up for the CONUS. However, this is just limited basically to major stations. And I've got a map here just as an example that shows precipitation totals through the month of May 2015. And so, of course, each of those values there corresponds to a station. So it's a pretty good network across the country, but unfortunately we don't have enough horsepower right now with this tool to run it for every single station there in the CONUS.
Okay, Chip, we'll add that to our website, those URLs as well for folks.
Okay, thanks, Henry.
Yeah.
Okay, so so now what I want to do is go in and start talking about the climate of the southeast. And so basically the sort of things that I want to emphasize here in this talk is really an emphasis on the geographic patterns of variability in the climate, also the variability in it over time and the trends over time. Obviously there's a whole lot of interest in this because we know that the climate is warming. I'll say some things about the societal and economic impacts, particularly of extreme events, and also speak in some ways to how they're a bit unique in the southeast as compared to other parts of the country. And then lastly, that second number 3 there, future projections of extremes. I'm just going to take a few minutes at the very end of the talk to say some things about those projections, and then that will conclude the talk. And I think one thing here that I want to bring out here to begin with is that there's many different definitions of what constitutes the Southeast U.S. or the South. And we're going to kind of basically focus on 2 areas, the CIRC region that I pointed out, CIRC being basically the coverage area for our center, but also the Southeast Climate Assessment region here. And I'm moving forward here 2 slides because I want to illustrate this. But basically, as I pointed out, our region for the CIRC extends from Virginia to Alabama to Florida and also includes Puerto Rico and the Virgin Islands. I played a big part in the Southeast Climate Assessment several years ago, and so a lot of the graphics that I'm going to show you include not just basically the Southeast here, but also this broader area of Kentucky, Tennessee, Arkansas, Mississippi, and Louisiana. Okay, and so again, I'm going to be focusing on different extremes, and so you see a lot of these here. This is one thing that really characterizes the Southeast climate, is that we experience a wide variety of extremes. And for those of you who are not in the region, you may or may not know that the northern parts of our region can get significant snow, and we don't get snow that often. And so when we do, as you can imagine, the impacts are somewhat greater. And so the other thing about the Southeast, no matter how you define it, is that we basically have more billion-dollar disasters than any other part of the country. Now, if you look at it on a state level of this map, you can see that Texas really stands out. They've had the most events, but that's just an artifact of Texas being a very big state. And so So Texas is #1 in a lot of things, and that's because of their big area. But when you look at it on a regional scale, the Southeast does indeed stand out. And if I were to show you a list of these billion-dollar disasters, you would see that more than 3/4 of them are hurricanes that have made landfall and go inland. And so that's one of the things that I'll be talking about here in the talk. We look at fatalities from extreme events in the Southeast, and these are sort of ordered from left to right. Hurricanes have seen the most fatalities, followed by tornadoes, flooding, etc., going all the way down to winter storms. What's really fascinating here about this is if you drill into the hurricanes and you look at it on a case-by-case manner, you find that Hurricane Katrina was responsible for the vast majority of these deaths. And these are just deaths from 1995 to 2010. And what this says here is that if Katrina had not occurred, that the number of deaths from hurricanes would be much less than the number of deaths from tornadoes. And so this really kind of points out that when you get really extreme events, sometimes the influences can be exponentially greater. And we know, of course, that the vast majority of the lives that were unfortunately lost there had to do with the failure of the levees there in New Orleans. And so that really was an infrastructural failure there. But when we look at these really big extremes that we experience here in the Southeast, when we think about fatalities and economic damage and so forth, we have to really pay close attention to infrastructure and people's behaviors and so forth. And so again, that's something I'll be talking about as we go through these extremes. So just to start off in very general terms, this is a map here over the broader Southeast and adjacent regions showing average annual precipitation. And I want to put this up here to just illustrate a couple of things. One is that there's this area in the southern Appalachians right along the North Carolina-South Carolina border extending to extreme northeast Georgia. This is the wettest region in eastern North America, okay, and it's extraordinarily wet. And so basically this is an area here that sees well over 80 inches of rain a year. And what's really fascinating about this is if you go off basically to the northeast and go up into the Asheville area, into the French Broad Valley, those are places that get less than 40 inches rain a year. So there's actually a doubling of rainfall over a very short distance here. So that's an extraordinarily wet place. We also look down here along the Gulf Coast, basically the western panhandle of Florida into southern Alabama and southern Mississippi. That is a very wet place. And then there's also some areas that are relatively wet. But looking in terms of dryness, you may not know that this area down here around Lake Okeechobee here in South Florida is a fairly dry place that averages just 30-some inches of rain a year. And really, though, the very driest place in our region is up here in this area. This is the Shenandoah Valley of Virginia, kind of going up through here. We go a little bit to the west, and this is sort of the valley and the ridge, and it extends a bit there into West Virginia. These are areas that are rain-shadowed, that the prevailing winds, which we know, winds tend to blow west to east. The air goes over the mountains, and oftentimes it gets dried out. Areas typically, when they get rain, they're getting basically moisture from the Atlantic Ocean or perhaps Gulf moisture that's sort of wrapping around this way. So anyways, very substantial differences in annual precipitation across the region. It's very interesting if we break this out and we look by season, and I'm just going to focus real quickly on 2 seasons. This is the pattern that we see during the winter. This is meteorological winter, so this is December, January, and February. And of course, what really stands out here is that the western portions of the Southeast, basically the southern U.S., sees more rain than any other area. And especially going down here into this area here into central Alabama and Mississippi, this is an extraordinarily wet area. Mind you, this area up here around the North Carolina, Georgia, South Carolina border is extraordinarily wet as well. And there's locations here that get as much or more rain here as maybe some locations down here in this area. So very wet. In polar contrast to that, it's quite dry down here in South Florida. And South Florida in particular experiences a very interesting climate. Basically, they have a wet season during the summer, and they have a dry season during the winter. And so very pronounced. And so there's places down here that get less than 5 inches of rain during that wintertime period. Another area that really stands out again is the Shenandoah Valley in Virginia here, kind of right up here in this area. And basically, they're sheltered really no matter what direction the winds blow from. So even when there's moisture coming out of the Atlantic here, you've got the Blue Ridge Mountains that that air is forced up the Blue Ridge, and so you get what's called orographic lifting. That wrings out some moisture in the air, and so when that air then sinks down into the Shenandoah Valley, it dries out, and of course there's basically not as much precipitation. Real quickly, I just wanted to illustrate this a little bit in terms of where the air typically comes from, and so I've just drawn some arrows here. I call these moisture trajectories, and the thickness of the air basically corresponds to how frequently they're observed in a typical winter. And so winter, our winds really prevail from the west and the northwest. So they're very common wind directions. And the result of that is that these areas here in the plateau of West Virginia, and then basically the west slopes of the Appalachians going down this way, they see more rain basically than areas off to the east. And so a lot of times when they get rain, and in a lot of cases, of course, in the higher terrain, it falls in the form of snow, it occurs frequently, but it's typically not that heavy. Because obviously trajectories coming this direction, there's not much moisture with the air. Now it happens less frequently, but still every winter you get a number of big cyclones that basically move across the country and they pull in Gulf moisture. And so I just showed two examples of trajectories here. So moisture coming out of the Gulf, moving northward and then northeastward up into this area. And then sometimes when cyclones are moving farther south, and they're actually moving across the southern U.S., the center of the cyclones, you can get moisture it's basically turning in a counterclockwise fashion around like this, and that can give very heavy rain here along the basically the east slopes of the Appalachians or the Blue Ridge front here in particular. And then one last arrow just to point out is you've got the Atlantic here as a moisture source region, but typically we only get Atlantic moisture when we have low pressure cyclones moving across this way, and then that pulls in a lot of moisture off the Atlantic. And when that occurs, these areas can get a lot of rain. And if it's cold enough, they can basically get a whole lot of snow. Fast forward to summer, and we see a very, very different pattern of precipitation across the region. And what really stands out like a sore thumb is Florida in particular, but especially this area down here in basically southwestern Florida, so a little bit east of Fort Myers. Okay, so this is an area that sees more than 35 inches of rain in June, July, and August. Very, very wet. And Florida in general is wet. It is their wet season. If you look at this, though, very closely, you see there are substantial variations. And if you look here right along the coast, you see some dark green, in some cases some lighter green. And so we're talking about maybe on the order of 14 to 16 inches of rain here right along the immediate coast. You can't see it along here, but there's actually some little bits of green around the edges of Tampa Bay here. And so just a short distance away, they get much, much more rain. More than a doubling of rainfall on average. And so it's a very interesting phenomenon down there where we have basically sea breezes that migrate off the Atlantic. So air basically blows off the Atlantic during the day. Indeed, the trade winds are blowing this direction, but you get the sea breeze that enhances that easterly flow. And that air moves across, and then that air then convects over the land. And then, of course, that's when you get the showers and the thunder showers that produce a lot of this rain. While all that's going on, a sea breeze develops along the Gulf Coast. It doesn't make it very far inland because it's going up against the trade winds. And so you get a lot of convergence of this really moist air. And that air converges in the interior of Florida. And this happens most days during the summer. And so that, of course, produces a very, very wet climate. To a lesser extent, we see this as we move up along the southeast coast here. So there are big differences in precipitation between being right on the immediate coast here and going several miles inland. So 1.5 and to some cases a doubling of precipitation over a very short distance. So in this case here, again, there's the sea breeze that develops on most days. Sea breeze moves a few miles inland, and the air basically convects up on the edges of that sea breeze, produces the showers and the thunder showers that produce a lot more rain a little further inland. And we see these relatively dry areas up here. Some of these have to do with rain shadow, but it's not quite as pronounced as what we see during the wintertime. I'll just point out one last feature, the southern Appalachians. The edge of them is right here. It's called the Blue Ridge front. And you can kind of pick it out here in terms of precipitation. So right along the edges here, so we've got the Piedmont here to the south and the east, and then this ridge that's 3,000 to 4,000 feet high here. And so air basically rises up and convects up over that ridge, and so you end up with a lot more precipitation there in some cases than you do in the Piedmont or in the intermountain parts of that area. Okay, so moving forward here, if we look at precipitation over time across the southeast, this is the broader southeast that includes Louisiana and Arkansas, and we see that in precipitation over time, what really stands out here, both annually and just for the summer, is a lot of variability from one year to the next, but no long-term trend in precipitation. However, if we go and we focus on precipitation extremes, basically the frequencies of heavy rain have been going up over this time period. I don't have time to go in and talk about how Ken Kunkel at the National Center for Environmental Prediction, how he developed this, but this is a good measure here of the frequency of heavy rainfall. And again, we see a lot of variability over time, a lot of up and down, but the long-term trend is a positive one. And this is one of these things that is consistent with global warming. We know as the atmosphere warms, it can hold more water vapor. We know that large bodies of water have warmed up a slight amount, so there's a little bit more evaporation. So having heavier rain is certainly consistent, with that idea there. Now let's moving over to the other side of the hydroclimate here. If we look at droughts, and in particular we focus on what are called hydrological droughts. These are droughts that tend to be of a longer duration and result in the water table basically lowering over time. And these bars here, the height of those bars basically corresponds to the number of months in which the region was in hydrologic drought here. And I just selected one region, and this is basically this pattern we see across much of the Southeast. So this is a climate division here in North Carolina. And so this is a time series that starts back in the very late 1800s and goes all the way up basically through the year 2011. And so where the bars are high, those were very droughty years. And what we see here is that there was this period basically in the 1920s all the way up to the early 40s where we saw quite a bit of drought, but particularly in the late 20s. So this general period here corresponds with when the Dust Bowl occurred in the central part of the country. And so we had some really major droughts there, and when you look at this particular one, we see that basically there were two droughts there that were more severe than any of the droughts that we've had in more recent years. And so basically there's been no long-term trend here in the frequency of drought. And again, this is a pattern that we see across much of the Southeast. One thing you will notice, though, that's kind of interesting and stands out is that there was a period in the middle part of the 20th century where there were fewer droughts. And in a number of different ways, there were fewer extreme events that occurred, say, in the 1950s, 1960s, and early 1970s, at least for certain types of extreme events. So it was a relatively quiescent period over much of the southeastern region. Okay, I just want to illustrate something about drought in the Southeast that really stands out. The southeastern region has really saw major population increases. So we have Atlanta. Here in North Carolina, we have the rapidly expanding triangle area that includes Raleigh. We have a tremendous amount of coastal development that's occurring. And drought is a huge issue here in terms of water resources. And with all these people moving into the area and all the development, we're using a lot more water, and our infrastructure isn't necessarily built to withstand the droughts that we typically experience. And so it makes it easier to go into drought. And so there was a term that was tagged called flash drought, when a drought pops up very quickly. And so this happened to occur in the year 2007. And you can see here in this upper panel, this was a drought that was concentrated in the Carolinas. It also extended into North Georgia and affected some parts of Alabama. Okay, so this was basically a regional drought. What's really interesting is there was no drought at the beginning of June of 2007. And then it got fairly dry. And then when we got into August, we had a major heat wave, which greatly increased evaporation rates. Very, very quickly, we went into drought. And I just show a picture here of the major source of water for the city of Raleigh. This is Falls Lake Reservoir. And you can see how incredibly low basically the water had gotten here. So this is something, no matter what kind of changes we see in precipitation in the future, because of the continued population development, this region is going to become increasingly sensitive to droughts. And also, too, just lastly, I'll mention in coastal areas, it's really problematic because when we go into drought, basically you get saltwater intrusion happening more frequently. And of course, that's going on just in a normal climate, but any kind of drought, much more salt basically can get into the water. Okay, so moving on here to temperature, and I'm just going to cover this very quickly. So just two maps here showing typical temperatures, and I want to show this here just to highlight that there's tremendous variability across the South. Obviously, in the wintertime, South Florida is quite warm, and it gets really cold, in the Appalachian Mountains up at the higher elevations, particularly in this area up here along the western edges of Virginia and West Virginia. So these are areas that with elevated terrain. Also, prevailing winds out of the west. There are lots of cloudy days there. Okay, and so you don't get as much solar radiation and so forth. So big changes in temperature, just climatologically as you go north from Florida, truly up in the mid-latitudes. A whole different pattern when we look at it here during the summer. We see this broad area. This is average July max temperature. Broad areas, the average daily temperature is basically in the low 90s. Okay, in all these red areas. What's interesting is if you look right along the coast here, the averages are below 90. So again, the sea breeze, when it migrates in on these summer days, there is a slight cooling effect. Of course, there's a cost with everything, and the cost there is higher humidity. And so while the air temperature is cooler, there's more moisture in the air, and so that makes it feel more uncomfortable. Up here in the highest elevations of the Appalachians, in contrast, daily max temperatures in some cases just get into the low 70s. And so these are places that are up at 4,000 and 5,000 feet elevation. Okay, and so if we look at temperatures over time, the Southeast has a very interesting temperature pattern where if we look at it from the late 1800s all the way up to just a few years ago, there's been very little net change over that long time period. But what we've seen is a very slight increase over the first half of the 20th century, a marked drop in temperature starting in the 1950s and going through the 1970s, even early 1980s. And then the temperatures have really been climbing since then. And so when we compare that with other parts of the country, it's kind of a unique signal. So basically the Southeast temperature trend is expressed here. We look at it across other areas, even just compare it with the U.S. average. Here you can see with the U.S. average, there's been a very slight increase and then a very marked increase here in time. But other parts of the country, you see basically a more marked warming in time. And so there's been some research done in trying to understand why temperatures in the Southeast haven't warmed as much as other areas. One interesting hypothesis has to do with the fact that there's a lot of coal-burning plants. This is particularly in Tennessee and Alabama. And basically the particulate matter goes into the atmosphere, and the prevailing winds carry that eastward across the region. And so that particulate matter reflects away a little bit of the shortwave radiation coming in from the sun. That induces a cooling effect. Well, fortunately, our air is getting cleaner and cleaner. And but what that means is with less particulate matter up there, we're getting a little bit more sunlight. And so that certainly is contributing, at least in a small way, to that we're seeing more of a warming now, and maybe we didn't see as much of a warming earlier back in the 20th century. Okay, so cold air outbreaks, if we look at them over the broader region, don't have time to go into how this index was computed, but I just want you to focus on the peaks here. So these are basically years in which there were some really extreme cold air waves here. And what we see is that they've occurred, periodically through much of the history of the region. Okay, but there's been a real decline since the mid-1980s. So we had, by some definitions, the coldest air in 100 years that occurred in January 1985. Okay, but since that time, we haven't had any outbreaks that are really comparable. We had one a couple of years ago. It was pretty extreme, but it didn't quite get up there. But anyway, you see that there's been a clear reduction in the frequency of the most extreme outbreaks. It's interesting, however, when you go back and you look at the end of the 1800s and 1900s, while you've had some of these extreme outbreaks, the frequency of moderate outbreaks hasn't been that great. Okay, but when we look at the latter half of the 20th century, there are quite a few winters where we had quite a few serious cold air outbreaks. Okay, and in terms of winter weather events, this is a real busy diagram, and I just want to point out just a few things here in this diagram. So this basically presents snowstorms, Arctic outbreaks, and ice storms across the Southeast. And this is the smaller Southeast region for the climate that the Climate Center serves here. And where you see these reds, these represent years, or basically winter seasons, that were in the top quartile in terms of the occurrence of these events. And so we kind of go through time starting 1950 all the way up, and this goes up to about, I think, 2008. And so we look at the patterning here in the reds. And so if we start off with snowstorms, we see that the Southeast, and this will, of course, will be the northern parts of the Southeast, saw lots of snowy years from the late 1950s all the way up to the late 1960s. There was a lull through much of the 1970s. And then there was this other period in the late 70s and early 80s where we saw quite a few. But look, since then, there's been very few years that are really exceptional in terms of snowstorms. Kind of a similar pattern with Arctic outbreaks, and the fact that the later years, there have been few years that have been extraordinary in terms of the intensity and the frequency of Arctic outbreaks. Ice storms, interestingly, is a bit different. They seem to be more randomly scattered out over this period, and so we've seen more than our share of ice storms in the Southeast from the 1990s, at least up through the late 2000s. You can see this period in particular, the late 1990s and through much of the 2000s here, quite a few big ice storm years. And one could hypothesize from that that the climate's warmed a bit and events that would have been snowstorms ended up being ice storms instead. Okay, in terms of heat waves over time, interestingly, you would think with the, with the warming of the climate that we would see a huge uptick in the number of heat waves, at least across the broader Southeast region. There was this period here in the early 20th century where there were a lot of really major heat waves. And so if anything, we've seen a bit of a downward trend, at least in the most extreme outbreaks. What you can say with confidence, though, there's certainly been no trend. If anything, maybe a very slight downward trend here. Now, one caveat here with this is when we talk about heat, we also need to talk about humidity. And of course, humidity plays a big role in the Southeast. And so this is just purely air temperature. And I will tell you that these heat waves back in the early middle part of the 20th century, that air was relatively dry. So that was air that was coming from droughts that were occurring, you know, over Texas and Oklahoma and so forth. And so that air was maybe not as uncomfortable as, you know, hot air that we've experienced in more recent, but slightly cooler heat waves. Okay, so moving on here to hurricanes. As I already pointed out, hurricanes have caused, you know, really more damage, and there's been a lot of lives lost and so forth. Fortunately, we have a very excellent warning system now, and so very few people die along the coast. And so we think about it in terms of impacts. You know, storm surge is way up there. So it turns out now that for the Southeast and for the country in general, that more people die in inland flooding from hurricanes than actually die from storm surge. What's really problematic economically and is also a danger to life is the strong winds of hurricanes that move inland. And of course, obviously, there's structural damage to houses, but the big thing is that the Southeast has lots of trees, and because we have a relatively mild, warm climate, trees grow more quickly. And at least in areas of the Piedmont and the coastal plain, we have lots of what are called loblolly pines. They grow very, very quickly. You see them in a lot of residential areas. And when you get these strong winds with hurricanes, those trees either break, and if the soil is wet enough, sometimes they come down by their roots. So people have been killed by that. People have been driving in cars as trees have come down, and of course lots and lots of power outages. And so that's been very significant. And also too, just again pointing out heavy rainfall, lots of inland flooding. If I had more time, I would give you some examples of that. Okay, this is a map from the National Hurricane Center, and this basically shows what's called the return period for hurricanes. And basically what you see here is where you see the reds, this is where the return period is the shortest. These are areas that see hurricanes the most frequently. And so you see here 5 years here. This corresponds with Hatteras. So when you average out over really long time periods, on average you would expect a hurricane to basically make landfall within 50 nautical miles of Hatteras once every 5 years. And that is in stark contrast, let's say, down here around Jacksonville, Florida, where it's 13 years. Okay, so basically there's almost a threefold difference here in the return period. And just generally, though, the pattern you see is that areas that really stick out in the ocean, those are obviously areas that get struck by hurricanes more frequently. And you see that pattern also here around Louisiana. If we look at U.S. hurricane strikes by decade, and this includes not just the Southeast, but also the southern United States, we see over the long period here, there really isn't a trend. Okay, so we've had, it's really been variable from one decade to the next. But what really stands out here is that there's basically a cycle. Okay, and so we see that there was basically a peak here that occurred in the 1940s, and then there was a lull that really sort of was really there the most in the 1960s and 70s, and then it's basically has picked up again. And it turns out that this cycle here corresponds perfectly with a natural cycle that's seen in the Atlantic surface, the sea surface temperatures. And so there's periods in which the Atlantic is slightly warmer and periods in which it's slightly cooler. And so the periods where it's warmer corresponds with increased hurricane activity, and where it's cooler, decreased hurricane activity. And so there are other factors too that control how many hurricanes develop. A number you probably know about El Nino, and we had a very strong El Nino this last year that's now dissipated. But when we have El Nino conditions in the equatorial Pacific, that causes the wind speed in the upper part of the atmosphere over the Atlantic, and anyway, that really hinders hurricane development. So there's a number of factors that control this, but really what we see is variability to this point, and not any positive long-term trend in the frequency of hurricanes. Now moving over here basically to tornadoes, show you here real quick, and probably a lot of you have seen a map like this here. This is basically shows areas that see hurricanes the most, or tornadoes the most frequently, and so clearly a tornado alley stands out. Texas basically going all the way up here into the eastern Dakotas. What I want to point out is that Florida actually sees just as many tornadoes in an average year. Okay, and the Southeast does get tornadoes. Now the map over here on the right, this basically illustrates the frequency of tornadoes that have killed people. And so a term has been tagged here called Dixie Alley. So basically strong tornadoes that kill people occur more frequently in this part of the country than anywhere else in the world. Okay, and so what's the deal here, and why do more people get killed in this area? And I'm just going to show here, this is another depiction here. This just shows the number of tornadoes that are EF2 and greater. So these are basically strong tornadoes. But what's really unique in the Southeast, let's say, in relative to the Great Plains is, one is that unfortunately there's a lot of poverty in the Southeast, so there's a lot of people who live in substandard housing, mobile homes and so forth. And obviously that's not a good shelter to be in when hurricanes are coming. Another factor too is that the Southeast, and I already mentioned it, there's lots of trees. And that's problematic in several ways. So when tornadoes come through the area, they're knocking down trees. That causes more damage. Moreover, trees obscure the visibility. So it's hard to see when a tornado is coming if there's a lot of trees around. So you don't see nearly as much of the sky as what you would see basically in the Great Plains. And the third thing, and of course it relates to the second one I talked about, again, the poor visibility, many trees. Typically, climatologically speaking, when you get tornadoes in the Southeast, typically they're accompanied by low clouds and a lot of precipitation. And so the low clouds and precipitation can completely obscure the tornado. And so you just don't see it coming. Another thing is a lot of the tornadoes occur basically during the cooler months of the year. We have a second maximum in November. We've had some really infamous tornadoes that have occurred then, but also really going through the winter, January, especially February and March as we're headed into the spring season. That time of the year, when you get tornadoes, they tend to move very quickly. They tend to be bigger, so they're more dangerous. Also, a lot of them occur at night. And so, of course, during the wintertime, the sun sets earlier. A lot of these tornadoes occur at night, so again, you just don't see them. When the tornadoes occur in the middle of the night, people are sleeping, and they may not even get the warnings. Okay, in terms of tornado trends over time, this is a time series here. This basically starts 1950 and goes up through 2010, and I put 2011 up here as a start. The year 2011 was extraordinary for tornadoes across the United States and the Southeast here. But what really stands out here is that there was this period here in the 1970s, some extraordinary years. I remember one of them really vividly. I was living in Virginia at the time. The super outbreak of tornadoes occurred April 3rd and 4th, 1974. There were a number of major tornado outbreaks there, but very interesting climate back then. But the big point here is that we haven't seen any upward trend. And the year 2011 was just amazing. But since then, if I could extrapolate this here, we would find that the bars would be back down here. So again, no positive trend in the frequency of at least strong tornadoes. Looking real quickly at severe thunderstorms, the Southeast sees more than their share of severe thunderstorms compared to other parts of the country. Obviously the damaging winds there, and again, I'll point out trees that are in the area, and trees coming down are a big danger. We certainly have our share of large hail, although I'll say, large hail occurs with the greatest frequency basically in the Great Plains. We certainly get that here. There's a lot of agriculture in the Southeast, and so hail is a big problem there. Lightning really stands out as well, and I'll say a couple things about that here. So if we look at the broader Southeast region, and if we look at the number of people who die from lightning strikes, interestingly, New Mexico stands out there as being number one. But I've highlighted all states in the broader southeastern part of the country, and it turns out that 8 out of 11 states in the Southeast are basically in the top 20, in terms of lightning deaths per year. And there's two reasons for it. One is that, of course, we experience a lot of cloud-to-ground lightning in our area. The other thing is that we have a lot of agriculture in our area, and so basically, people are outside, they're exposed to lightning. Of course, we also have a lot of golf courses, and we've had more than our share of golfers who unfortunately been struck by lightning. We look at this flash density map here. So flash density is just a fancy term here for the number of cloud-to-ground lightning strikes. And so we have a very sophisticated cloud detection network here. Okay, but we see huge variability. Florida, again, really stands out. We know that Florida gets more rain, and especially during the summer when it's convective, when it's falling in thunderstorms and so forth. So that's where we see the greatest frequency of cloud-to-ground lightning strikes. This generally goes up here along the coast, and I should say just immediately inland of the coast. The immediate coast, basically because of the sea breeze, basically doesn't see storms as frequently. So just the interior coastal plain here sees a lot. And then this area really stands out here along the Gulf Coast. Interestingly, when we get into the Appalachian Mountains, the frequency of cloud-to-ground lightning strikes is markedly less. But I will tell you here, at least in western North Carolina, there's a high frequency of thunderstorms or thunder showers. They just don't produce that much cloud-to-ground lightning. Okay, real quickly, and I just have a few minutes left here, and what I want to do is say some things about how the climate is changing and basically what the projections are as we go into the future. And so just first off, to make a couple of general statements, and I've already alluded to this earlier in the talk, the projected changes that we see in the Southeast are not as great as those observed in other parts of the world. And given that that's the case, I think that when we think going into the future about being vulnerable to weather extremes and so forth, that we need to really think in terms of climate variability. We need to think in terms of the past. And so there's a basic sort of climate law that anything that's happened before can happen again. And so we've had some incredibly extreme weather events in the Southeast. We've had them in the past, and unquestionably we're going to have them in the future. Okay. The other thing I want to say here too is that there's much uncertainty in the model projections. And the models, the general circulation models that are used to come up with these projections, they have gotten much, much better, okay? And there's some that I would almost hang my hat on, at least maybe when it comes to temperature. But when we look at other meteorological variables, there's really some uncertainties there. And so I think that's something we really need to remind ourselves. And so we don't think of these models in terms of making forecasts like we would make weather forecasts, but rather it's better to think of them in terms of scenarios, what they call projections. And so with those caveats there, let's look at these. So first off, starting here with temperature. Okay, so basically these slides I'm showing you come from the National Climate Assessment. And so this has been vetted by lots of scientists and so forth. And so what I'm showing you here basically are projected differences in temperature between a future period. And so we look up here, this future period runs from 2041 to 2070. So this is basically the middle to late part of the 21st century. So they're taking those values in terms of temperature, okay, for annual temperature in the Southeast, and subtracting from that the average temperature from 1971 to 2000. So this is kind of like the base. And what we see for the entire region is that it's going to be warmer. So this period here, warmer than that one. We can see the degree of it here in terms of the hotness of the colors, and what we see annually is that the northern parts of the region are projected to show greater increases in temperature than the southern parts of the region. What's really interesting, though, is if you break it out by season, and if we look basically during the winter time, it's kind of we basically see that there's more warming basically in the northern parts of the area, but this is especially the case during the summer. And so in terms of seasons, we expect relatively more warming during the summer months than during the winter months. And that's very much a problem, when we think about it in terms of energy, energy for air conditioning and so forth, but also in terms of heat illness and also mortality from heat. And obviously, the farther north you go, the less acclimatized people are to the heat. And so that certainly is a big concern here. I guess one other thing, too, I should mention in terms of these projections, these are basically projections from lots of different models that have been averaged, together. Okay, so flipping over here to precipitation, so kind of the same kind of deal here. So we're taking the projected average amounts of precipitation during this later period and subtracting the base period here. And what we see here for most of the region is an increase in the annual precipitation, rather modest, anywhere from a little over, let's say 1%, maybe going to upwards of 4 to 6%, something like that. I will point out down here in South Florida, they're actually projecting decreases in precipitation, and likewise down here in Louisiana and parts of Arkansas. When we break this out by season, we'll just show here that the increases in precipitation are projected to occur somewhat more during the winter and to a lesser extent the spring months. Okay, so wetter winters. Okay, but when we go into the summer, a lot of the area there's little change. But what's a little bit disturbing is when we go back and we look here in these more western areas, we're seeing in some cases a projected marked drop in precipitation. And so of course during the summer it's already hot. We know it's going to get hotter. And so you connect that with less precipitation. That means perhaps a big increase in the frequency of drought in this area and also down here in this area of South Florida. Okay, just focusing on heavy rainfall. Okay, so this map here basically shows the changes in the number of days that we would experience 1 inch or greater. And it shows that really for much of the area there's expected to be an increase in heavy rainfall, but basically that increase is expected to be more up here in the northern parts of the region here. Okay, and real quickly here with droughts, no clear trend for the region as well overall. Again, pointing out South Florida and also parts of Louisiana and Arkansas, certainly that appears a trend of more dryness. But the big thing to point out here is that the vulnerability is increasing due to population growth, among other things. In terms of hurricane projections going into the future, there's been a lot of research done on this, but I think if researchers could agree on something, they could agree that on the basis of what we've learned so far, we would expect a slight reduction perhaps in the frequency of tropical storms and hurricanes overall, but disturbingly, an increase in the frequency of strong hurricanes. You might think that doesn't quite sound right, and you think about it, if the hurricanes get their energy off the ocean, and unquestionably the oceans are warming up and will continue to warm up. But there's one sort of fly in the ointment, and that has to do with something called wind shear. The upper level winds over the Atlantic, as the climate warms, are projected in a lot of models to increase. And that's something that basically inhibits hurricane development. But the general idea here is that as we go into the future, those winds increase. There's still going to be a lot of variability in those winds. There's still going to be hurricane seasons in which those winds are relatively weak, and when they are, there's a warmer ocean there. And so when that occurs, stronger hurricanes can develop. But overall, if you look at overall frequencies, over many years, perhaps a slight decrease there. And then lastly, just mentioning here briefly, sea level rise. So there's a tremendous amount of coastline along the southeast here. And this here basically shows projections of sea level rise. So this actually goes back in the past a little bit, 1990, and going all the way up to 2100. And what this basically presents is an envelope of possibilities. And so if we look at this dark, basically part of the envelope, that's where the confidence is greatest, okay, in terms of sea level rise here. But according to this figure here, the sea could rise quite markedly and be way up here, but it's also possible that it could end up being way down here. So it's kind of like some people have called this before the cone of uncertainty. And one thing about this uncertainty that really drives it a whole lot is how the changes in how much emissions we're going to get of carbon dioxide going into the future. So in other words, if we really do end up reducing CO2 emissions, we're going to be more likely to be on the bottom end of this envelope. But basically, if it continues to be business as usual and CO2 levels in the atmosphere continue to increase, particularly in developing countries, in the next 50 years, we're more likely to be up here in this area. And I guess the last thing to point out here, too, and it's sort of identified here on this diagram, is that a lot of this sea level increase to this point has been simply from the thermal expansion of the ocean. So as the oceans get warmer, that water expands slightly, that increases sea level. As we go into the future, we know, of course, that the ice caps are going to be melting more and more. And there's a lot of uncertainty around that. And so, so if the warming continues up in the polar regions, you know, a lot of uncertainty in terms of how much ice melt. But if we get more ice melt than expected, then we could have a very, very large increases basically in sea level, because obviously as those glaciers melt, that meltwater goes into the oceans and in that way raises sea level. Okay, so that concludes my talk, and I want to thank a couple of people here. First, Jordan McLeod. So some of the graphics you saw here, particularly precipitation, he developed them here. He's the regional climatologist here at the CERC. Chris Furman was a former regional climatologist, so he assisted in some of the graphics. Maggie Kovac, she's now an assistant professor at Appalachian State. I also want to thank the North Carolina State Climate Office, Ryan Boyles, and his assistant Ashley Frazier, who developed some of the graphics that you saw here. Thank you very much.
Thanks, Chip. Really appreciate your giving us this talk today. Very interesting stuff. If you guys have any questions out there, it's time to go ahead and type them in. We've got a couple that have come in. Before we take those, I've got one for you. I've noticed that when I lived in the Southeast and along the Carolina coast and interior around Raleigh, the thunderstorms, the lightning seemed to be much more, the thunder was a lot louder and so forth. Is there anything been looked at on that? I know it's kind of an odd one, but boy, I remember going down to Myrtle Beach or down around Swansboro, down that area, and it knocked your socks off some of these storms.
Yeah, I mean, that's an interesting question, I think, around, you know, that maybe there's not necessarily more lightning, but when you hear you said the thunder actually sounds louder, and so that kind of gets to the acoustic environment underneath the storms. And I've noticed that sometimes, you know, if you get a thunderstorm in the middle of the night and you hear the thunder, it sounds more like a sonic boom or a gunshot or something, and that in those cases, there's low-level clouds, and they're acting as mufflers. And so, but I think sometimes there might be a just right kind of thing where you know, in the Southeast it is more moist and you have lower cloud bases, but below that cloud base, maybe sometimes you could perhaps get some ducting of the sound or something like that.
Yeah, I guess since we live out west now, they're not that noisy. I mean, a big difference I've noticed, and it could be the dry air with the wet air and the acoustics from that. So. Well, here's a question. John in Texas wants to know if there are any published recommendations on when a municipality should sound outdoor weather alert sirens, and for the duration of how long that should be.
Yeah, and so I mean, I'm presuming when, you know, severe weather is coming, like a tornado warning or something like that, and you know, and I'm not really the person to ask about that. I mean, I would think you'd want to keep it going there, but honestly, that's not a question I don't think I'm really well qualified to address.
Okay, Daniel writes in, and he was looking at the climate projections, and he was wondering why 1971 through 2000 was removed from those slides.
Okay, 1971 to 2000, it wasn't. In terms of the projections, that period was just basically used as a base period. So we're looking at the future, and you know, when I tell you, well, it's going to be 95 degrees on average, let's say here in North Carolina, you might say, oh yeah, that sounds hot, but you want to know how that compares with the past. And so the graphics that I was showing there basically was taking what the projected values were and subtracting a base period, which was 1971 to 2000. So it's not that it wasn't in the analysis, but it was just simply used basically as a baseline there for comparison.
Yeah, and Ricky also wanted to know what the definition of threshold was for that.
Okay, threshold, and I would ask the question: what in threshold in what context? A threshold for a change? I'm not really
maybe
sure.
he can maybe he can write in and be more particular on that one. Okay, let's go on to the next question here, and Eva wants to know if the sea level rise is high, as on the chart. What does it mean for saltwater intrusion?
Oh, that's an excellent question. And unfortunately, as the sea rises, you would expect there to be a much more saltwater intrusion. And right along the immediate coastline there, where the sea basically intersects the land, that seawater basically goes in the soil, and you see it, inland, down below. So it's basically a lens, as it were, a lens of seawater that goes inland. And so if sea level rises, you would expect to see that lens of salty water to go to be further inland as well. And again, that's a huge concern for coastal communities going into the future.
I was amazed. I was just in the Bahamas recently, and from Hurricane Joaquin, the saltwater intrusion that came into some of the estuaries, amazing damage done into some of the freshwater areas, and you can still see the remains of that. It was pretty bad. Here's one from Jim, and Jim wants to know what causes sea breezes to lead to interior storms in Central Florida one day and not the other. He says that sometimes they get them and sometimes they don't.
Right, and it's compared to other regions, they get it more frequently than any other place. But indeed, there's going to be variability from one day to the next. And so just in terms of explaining it in basic terms, most days in Florida in the summertime, in the morning, the sun is out, okay, and the land warms more quickly than the water. And when land warms up, the air is warmer, and so the air basically starts to convect upwards. And when that air basically moves upwards, then that draws the air over the adjacent, basically over the ocean. That generates the sea breeze. So this slightly cooler, more moist air then flows inland behind the air that's lifting convectively there over the land. And so that is the sea breeze. But the good question there is, well, why wouldn't you expect then clouds and showers and thunder showers to develop every day? And so there are a couple of things here. One is that there are going to be days in which the air aloft is somewhat drier. Okay, so there may be days in which the air may be several thousand feet up or higher. Basically, maybe it originated somewhat farther north, over the mainland United States. So sometimes the air is just so dry that you can get that circulation, and you actually get the cumulus clouds. The clouds look like cotton balls. You see them rising up, but they basically dry out near their tops, or they get stymied. There's an inversion there that keeps them from rising higher. But dry air certainly is a big factor. Another one is that there are going to be other days that there may be some weather disturbance, maybe a tropical disturbance that's in the region, and it's already generating a lot of clouds, and there's enough clouds that you don't get that much daytime heating over the land, and so you just don't get much of a sea breeze developing, and therefore you don't get these storms setting up in the typical way.
Thanks, Chip. Here's one from Joe, and he says he often hears talk of the Bermuda High over the area there in the southeast. He would appreciate your commenting on what that is.
Oh, that's a really good question, and when you just said it now, I thought, oh, if there was one thing I neglected to mention, it was the Bermuda High, because the Bermuda High has a huge influence on our climate, and when we look at it in general terms, when we're in the wintertime, the Bermuda High is relatively weak and it's well off the coast, and so when it's that way, then that allows mid-latitude weather systems, to readily go through the southeast, and so we get big changes in weather from one day to the next and so forth, go through cold periods and warm periods. But as we go into the summer, the Bermuda High basically builds towards the southeast. And so it's truly positioned over Bermuda. And there's a number of days in which it actually ridges in over the southeastern U.S. And so it exerts a big influence during the summer. And I guess what's really significant there is that when it's centered a little bit off the coast, the clockwise winds around it bring in a lot of moisture off the Gulf Coast, depending upon where you are, maybe the Atlantic Ocean. And so it draws in a lot of moisture along its periphery. And of course, that moisture with the daytime heating, causes a lot of the thunderstorms that we see. And then occasions in which the Bermuda High actually moves over the southeast. The Bermuda High itself is a dry feature. There's a lot of dry, sinking air in it. And so that really quells the convection. And unfortunately, what that means is it gets really hot. So it's hot and dry. And sometimes, especially along coastal areas, there'll be a lot of low-level moisture that can be trapped kind of in the bottom of the atmosphere. But yeah, excellent question, and has a huge influence on our climate.
Thanks. Here's one from Paul, and he wants to know what factors control the location of Dixie Alley. You mentioned that earlier in the talk about the tornadoes.
Yeah, and so this gets down to the particulars of, well, what do we mean exactly by Dixie Alley? And in one sense, there's a general region there that sees a high frequency of big, strong tornadoes, okay? And so in that sense, there's a Dixie Alley there that you see, and certainly particular time of the year in the cool season, more big tornadoes there than anywhere else. So that, in one sense, could define Dixie Alley. But there's another part of it, too, is that corresponds with a broad area, again, where there's lots of poverty. And so it's not just that you get big tornadoes, but you've got a lot of people who are more vulnerable when these tornadoes come. And so so in one sense, you can sort of define it socioeconomically as well, within those areas. But it's an interesting, though, just meteorologically, the meteorological question: why do you see, at least during, let's say, from November up through March, why do you see more tornadoes there, really, than any other place in the world? And why are these tornadoes big? Why do they move fast? And that has a lot to do with the storm track. That obviously during the winter months we can get big cyclones. Maybe they develop off the Rockies in Colorado or New Mexico. But these cyclones basically move across the country, and they pull a lot of really warm, moist Gulf air across this Dixie Alley region. And then with these strong systems aloft, there's very strong winds. And those winds are in the right configuration to cause what's called a lot of wind shear. And so climatologically speaking, just having that source of moisture and warm air there in the winter that's close by, couple that with this very active storm track with all the dynamics, all the winds, that's kind of the perfect recipe for generating lots of tornadoes.
Okay, here's one from Charles, and he wants to know how are land-grant universities helping farmers to plan for different growing conditions in future years?
Well, that's a question that's a little bit out of my realm here, but I do interact with the land-grant university in NC State a bit, even though I'm up here in Chapel Hill. And I know, that obviously, there's a tremendous amount of money in agriculture and an incredible amount of research that's being done on plants and their vulnerabilities to different extremes. And of course, there's a lot of genetic work and so forth that's being done. And so I can speak in very broad terms to that, but farmers, take changes in the weather very seriously, and as we think about the future and how that's going to change, there's certainly a lot of research that's going into that.
Well, Chip, thank you so much for answering the questions we've had, and we really appreciate you taking time out of your busy schedule. I know you're a busy guy to give this talk today. It was very informative. We'll have it up on the web on Monday, and hopefully folks will take a look at it that have missed the webinar today, but it'll be archived for years to come, hopefully.
Okay. Well, thank you very much for having me.
Our pleasure. Well, folks, mark your calendars and please join us for our next webinar, our next Weather Talk webinar. And that's not too far down the road here on Thursday, August 4th. And we'll be looking at the 5th in our 6-part climate series. And this time we'll be looking at the weather and climate of the northeastern U.S. with Samantha Borzoff of the Northeast Regional Climate Center. They're up in Ithaca, New York, and she should have some interesting information for you guys all about the Northeast. So don't forget to sign up on that. We'll have the registration available for that later on today. Finally, when you sign off today, if you'd please take that short survey, it's going to pop up on your screen. That'll help us, and we really appreciate that. So until early August, this is Henry Regis for the rest of the CoCoRaHS headquarters team saying goodbye and have a great afternoon.